We'll give it a few seconds for everybody to start joining. All right, let's go ahead and get started. My name's Andrew and I'm with Pluralsight, and it is my pleasure to welcome you all here to today's webinar on artificial intelligence. Now, throughout today's webinar, if you have any questions, please click on the Q&A button below, submit those questions, and we'll have a little bit of time at the end to go over those and answer them. I'm very excited today to hear from our expert speaker, Simon, who has over 3 decades of software development experience and is passionate about the latest development technologies. So with that, Simon, I'll let you take it from here.
All right, Andrew, thanks very much. And yeah, good morning, good afternoon, good evening, whatever the clock is saying where you are. It's time we begin, and welcome. So this is a webinar, so I'm going to give about 2 minutes on the clock for people to finish getting everything together and getting logged in and making sure they follow the right link and all the other things. But as this clock is counting down, for those of you who are here and ready to go, well, first, thank you for coming. I'm Simon, I work for Pluralsight, and this will be AI, the introduction you always wanted. I'm going to talk about the problems with this title in just a moment, but it will be a short, pragmatic, practical introduction to artificial intelligence. And my whole goal for this session is that by the time we're done, which will be in about 40, 45 minutes from now, I hope you think, that was great. That was a really good use of my time. And I said in about 40 minutes, 45 minutes, this could of course go longer, but you know, it's a lunchtime session for some people. It's Friday. We've all been going for a while. We're full of Zoom fatigue and quarantine burnout, whatever you want to call it. I get it. So right now, whatever attention you're capable of bringing to this, thank you. I don't take it for granted, and I'll do my best to make this worthwhile. And, dare I say it, even interesting, because this topic is interesting. I mean, let's face it, there's not a lot of areas of computing that they'll actually make movies about, but they will do it about artificial intelligence. AI is inherently newsworthy. It's dramatic. Now, it's also sometimes complicated and sometimes tedious and sometimes confusing or unintuitive or contradictory, but still always interesting. And if you'd like to be more engaged with these kinds of subjects, recognizing and focusing on the parts of this you find most interesting is a pretty good approach. But with that, let us begin. This is a short introduction to artificial intelligence, and I called this talk AI, the introduction you always wanted. And you know, there's 2 problems with this title. First, it does sound totally egotistical. It's as if I'm saying, artificial intelligence might have been around for 50 years, but you know what it's been missing all along? Me, to come along and explain it to everyone. So no, that's not quite what I'm going for here. But as a longtime software developer and someone involved in education, I've seen a lot of introductions to artificial intelligence over the last couple of decades, and they usually fail in one of 2 ways. They either stay way too high level, and they talk about all the wonderful benefits and the hazards, but without actually saying how any of this actually works and how you can get more involved with it, or they fail the other way, and they immediately too focused on the specifics of algorithms and languages, but don't provide any context. So I'm going to do my best to keep it somewhere in the useful middle. So with enough about the basic ideas and also enough that it's pragmatic, you'd be able to walk away and know how to take the next step. But I said there were 2 problems with this title. And the second problem is the word introduction, because unlike some technologies, everybody already knows something about AI. Everybody has some ideas about this. You can't help it. AI is part of our culture. It's in our movies, our TV, our books, and our games. Even the earliest days of feature films, we had Metropolis. This was nearly 100 years ago. We had 2001, A Space Odyssey with HAL 9000. That was 50 years ago. But beyond that, we can think of Blade Runner, War Games, Terminator, The Matrix, iRobot, Ex Machina. You have been hearing about intelligent computers for decades, probably all of your life. And, spoiler alert, where AI always ends up wanting to kill everybody. Now, it's easy to think, yeah, but that's all fiction. I don't take it seriously. But when you're exposed to the same cliches again and again and again, we should recognize we have probably all unconsciously picked up some beliefs and assumptions about artificial intelligence. And I don't mean that everybody blindly agrees with the Hollywood idea of an inevitable dystopian nightmare future full of homicidal murder bots, but just more generally, we have absorbed some ideas and assumptions about what artificial intelligence means. What do we think AI is capable of? What do we think it's for? What do we think it's not capable of doing? And most people also have a few unspoken assumptions about how complicated this is, or how much of a computer nerd they have to be to even understand it. But here's the thing. Even if you've been, let's say, just aware of artificial intelligence for a while, you might also have a sense that you've been hearing a lot more about it recently. And not just in fiction, but also seeing AI mentioned in a lot more business publications, or seeing more conferences and events that deal with it, seeing it on more websites like AI being used for fitness, or AI used for music composition, or strange new devices that might not have existed before artificial intelligence, and also see it in conventional everyday products like this new AI-powered washing machine. But it is more than just hype and marketing speak, because we see an incredible amount of serious applications like AI being used in healthcare, being used in transportation, being used in finance. You'll see it in marketing, education, customer support. It is everywhere. So we're going to go on a tour of the most important ideas about artificial intelligence, see the different ways it can be implemented. We'll go over a lot of the jargon and the vocabulary, but focus on real-world applications, how AI is actually being used and implemented right now. And I'll cover a lot of the basic fundamental questions that people often have when they get started, like, what's the difference between artificial intelligence and just a really complex computer program? Is there even a difference? Or if AI has been around for decades, and it has, then why has it recently become such a big deal again? What happened? But we'll begin with probably the most common introductory question, which is, what exactly is artificial intelligence anyway? What does that even mean? Is there some simple, straightforward definition that we could learn and internalize, and from that point on, always be able to say, okay, that is artificial intelligence and that is not? Another spoiler alert, the answer is no. There is no one single agreed upon definition of AI that would always let us make that distinction. Now, I have a few textbooks on artificial intelligence. This one's 30 years old. This one's 40 years old. This one's 55 years old. It's been a serious field of study since the mid-1950s. And even in those very earliest days, they always admitted this basic phrase, artificial intelligence, is not simple to define. Not because it's difficult. We understand what those two words mean, but because with AI, the goalposts keep moving. This is a quote from an early paper on artificial intelligence from back in the late 1950s, where even then they said, it's not useful to lay down any absolute definition of intelligence because the goals are constantly changing based on what we've figured out how to do and how we're doing it. And through the entire history of AI, the entire history of computing, we've always had these goals, these aspirations that we've described that would require some kind of intelligence. Like, can a computer ever play chess at the grandmaster level? Or will a computer ever recognize faces? Or could a computer ever understand spoken commands? And we've figured out how to do all those things. But as soon as we ever figure out how to do that thing, the general response is, well, okay, but that's not really intelligence, is it? I mean, the computer isn't actually thinking. It's just executing a formula. It's doing a computation. There's even a name for this. It's called the AI effect. And it's that many technologies we now use every single day began as some kind of artificial intelligence research. But as soon as any part of this actually becomes implemented or practical and widespread, nobody will call it AI anymore. There are things you could do on your phone that a few years ago would have been considered remarkable, incredible applications of artificial intelligence. It's just one example. We have facial recognition that is so fast and accurate, I can turn myself into a 3D cartoon in real time. Now, if you had presented this at an artificial intelligence conference 10 years ago, you would have been the star of the show. But now we wouldn't even use the term AI to describe it. It's just something we can do on a phone, if we even care. There is no one perfect definition of AI that everyone will agree on. And that's okay. It's always been that way. But there's also one perception about AI you may need to deal with, because if you've been in the business world for a long time, let's say several decades, or you work with other people who have, it is not unusual for those folks to be a little skeptical and to privately wonder to themselves, didn't we already do this? Didn't we try artificial intelligence back in the 1980s and figure out it was a total waste of time? Because yes, there have been previous times where AI became massively popular for a while and then died out. I started programming in the mid-1980s, and at that time there were a lot of different artificial intelligence companies. We had companies like Symbolics and IntelliCorp and Neuron Data, even an artificial intelligence corporation. Now, if you're thinking, well, I've never heard of any of those. Yeah, exactly. Because to cut a very long story short, that period was a great time for most of the computing industry, but the entire AI segment of it completely crashed and burned. Most of the companies went under or pivoted away from it, and AI was generally regarded as a massive, massive failure. It had cost a ton of money, it had promised the world, and it hadn't delivered. And the impact was big enough that even the term artificial intelligence had a stigma about it. And for many years, if you wanted investment or funding, the last thing you wanted to say was you had an artificial intelligence project, because nobody wanted to know. And these periods are called AI winters. There's been more than one of them, where it's several years where there is just no money for it and no interest in it. And one of the reasons I talk about this kind of long roller coaster history of artificial intelligence is to realize why it has so much baggage with it. These misconceptions, partial understandings, things everybody kind of knows. And we have to identify and get past some of these cliches. And I don't mean the old AI will try and kill us all idea, but just common misunderstandings that get in the way. There are even visual cliches about this. Have you ever noticed that in our current culture, artificial intelligence has its own color? Apparently, we all think AI is blue. Now, if you're thinking, Simon, what are you talking about? Let me prove it. If you do an image search on AI to gather different pictures, different images from all over the web associated with this word, you'll find this incredible, bizarre consistency. There are tens of thousands of images created by countless different artists and designers, but they're all incredibly similar. They're mostly either a wireframe image of a brain made of interconnecting nodes and lines, or a robot, but not just any robot. The robot has to have a white plastic face, and for bonus points, exposed head wiring. So if I go to images.google.com, search on AI, you get node brain, white-faced robot with exposed head, node brain. It just keeps going. And notice almost everything is blue. And this isn't just true for images on the web. It's also true for book covers. And you'll see the same thing in articles and presentations. It's like all the graphic designers had a meeting and they decided, well, AI is blue, obviously. Now, okay, I'm poking a little bit of fun at this, but there is a point. I want you to start to notice these cliches. So the next time you see a book or an article about AI, and the first thing you get is a blue image of a robot with a creepy doll face that you think, okay, I've seen this before, so what other AI cliches am I about to get? And I think these kinds of images, that digital brains and plastic-faced robots, are actually slightly misleading and unhelpful. Because when we're talking about real-world, practical, applied, and business-focused AI, there's two things we are usually not trying to do. We're not trying to model a brain, and we're not trying to make a robot. There was a time when a lot of AI research took this neurobiology focus, and we thought success would only come if we could deeply understand the physical structure of a biological brain and then model it, creating software visions of the neurons and synapses. But while that is one approach to creating AI, it is not the only approach. And in fact, much of the practical successes of AI in recent years took a completely different approach, much more about statistics than biology. But while we are talking cliches, I said there were some useful ones. And next, I want to talk about perhaps the most common artificial intelligence cliche that you find in novels and TV and movies, which is in most fiction about AI, it's used to make a character. I mean, it's used to generate an entire personality with a wide range of abilities and skills. Sometimes that fictional AI is put in a body, whether it's humanoid or machine, and sometimes you just hear it. It's running on a computer behind the scenes and you interact with microphones and speakers. But in any case, where these AI characters are capable of complex, multi-layered conversation and behavior that's similar to, and possibly higher than, the level of a human. And where that AI character is not just capable of one specific narrow task, but instead is always generally intelligent, capable of many different skills, and capable of learning completely new skills by itself. And this idea, where AI is used to create the equivalent of a person, is actually known as artificial general intelligence, or AGI. It's also known as strong AI or full AI. Now, just to be clear, this is still hypothetical, it's theoretical. We don't have AGI yet. And this artificial general intelligence is not the goal or the expected outcome of much of the work that's happening in this. Although, we do have the other kind of AI. Some people call it weak. I prefer the term narrow, because it's not weak. Here we're talking about a situation where AI is used to be extremely powerful. It can often outperform a person, but only in one specific narrow ability. So we already have AI that can play chess better than anybody in the world. We have AI that's fantastic at spam detection. We have AI that can search massive amounts of data. We have AI that's great at recognizing faces. And all of these are getting better year over year. But these are all narrow AI. We understand that just because a computer program might be superb at detecting a spam email or recognizing an abnormal heart rhythm, well, that doesn't mean we expect that same program to also play chess or compose a sonnet or recognize or reveal the next TV show to watch. And that's fine. For the most part, we're not actually looking for general intelligence. What we want is specialized intelligence, narrow intelligence, because we're trying to use AI to accomplish or understand something in particular. We want a program that is task specific. But okay, if you're wondering, so is anybody actually trying to develop that artificial general intelligence? Oh yes, and not just some mad scientist in their basement. There is billions being spent on this right now. For example, DeepMind, who's now owned by Google, they're very specific that their aim is to build advanced AI, sometimes known as artificial general intelligence. Another example is OpenAI, who have billions of money and funding from Microsoft and Tesla and a bunch of others, and their stated mission is discovering and enacting the path to safe artificial general intelligence. But right now, AGI is still future-facing and experimental. So if we're focusing here on the more practical, applied artificial intelligence and what we can do right now, let's begin with one of the ways we can implement a narrow AI using machine learning. Now, because over the last few years, the most widespread successes and practical approaches for companies implementing AI has been using machine learning. Now, this success has even led to some confusion about the terms. Machine learning and artificial intelligence are mentioned together so often, it can make them sound like they mean the same thing, and they don't. As you're probably beginning to realize, artificial intelligence is a bit of a broad and sometimes vague term that really encompasses all the various approaches we could use to make a computer program do something clever. And machine learning is a set of specific techniques for achieving that. It's not the only way to implement artificial intelligence. So machine learning, or ML, is a type of AI. It is a subset of it. So all machine learning is artificial intelligence, but artificial intelligence includes additional techniques other than machine learning. And in regular conventional computer programming, we try and get a computer to do what we want by writing explicit rules into it, lots of if-then statements and very specific instructions. And make no mistake, conventional rule-based computer programming is great when you know what all the rules are and you're able to easily define them. But when we use machine learning, we try and get the results that we want, not by providing all these rules to follow, but instead by providing examples to learn from. Let's say I wanted to write a computer program that could recognize handwritten numbers, handwritten digits in an image. Well, let's make it even simpler. Let's say I just want to write a program to recognize the number 3 and all the various different ways it could be written. So if I took the conventional programming approach, I might try writing a program that would look at each individual pixel in an image one by one and figure out, is that pixel light or dark? And then try and think of all the different ways people might write the number 3 in a grid like this. Sometimes it's large, sometimes it's small, sometimes it leans to the left, sometimes it leans to the right, sometimes the top loop is smaller than the bottom, etc., etc. And that would be the conventional computer programming approach. Figure out all the rules, go step by step, try and envision every single eventuality. And to be clear, this would be very hard and tedious, and for this particular problem, really easy to get it wrong. But with machine learning, we wouldn't begin by trying to figure out and define all the different circumstances. Instead, we would begin with actual data. In this case, it might just begin with 1,000 different images of handwritten number 3s, and we would use this data itself to help build the program. So we take this training data, a bunch of examples of the different ways a 3 could be handwritten, and then we would feed that information into a machine learning algorithm, also called a learner. And this process is called training a model. And we'd often provide both positive and negative examples in our data. So here's a bunch of examples of the kind of thing we're looking for, and here's a bunch of examples of the kind of thing we're not looking for. And after we have trained a model successfully, we should then be able to take a new piece of input and categorize it based on the data we've used to train it. So if we show it a new handwritten 3, the model should say, yep, that looks like what you told me to look for. And if we pass in something else, it should say, no, that doesn't look like what you said you were looking for. And it doesn't mean the computer truly understands what the number 3 even is or how to write one. It doesn't. But we have provided enough examples that it can recognize the characteristics of that thing. And this is one of the tasks that machine learning is very, very good at: classification. And to be clear, classification is not just about images. It's about any kind of data. We could take the same idea into things like, is an incoming email spam or not spam by providing lots of examples of what spam looks like and what regular emails look like. Or if we had a bunch of, say, website activity data, we might be able to figure out the typical behavior of a high-value customer or of a fraudulent purchase and be able to recognize these different situations are happening based on what's happened in the past. We can get amazing results without having to program all the explicit rules the way we would have to do with conventional computer programming. But there is a catch. Machine learning is only going to work if you have data to learn from, and not just a little bit. You want a lot of data, and you want good quality data. It's why there's been such a focus on data collection and big data in the business world over the last few years. Because if you don't have good data, then you have nothing for your machine learning algorithms to learn from. Now, a common question at this point is, well, okay, Simon, if this all works by taking our examples of data and we feed it into a machine learning algorithm, well, what is that? I mean, where does this machine learning algorithm come from? And that's a great question. Because when you're new to this, you might think, okay, so do the software developers in my organization need to write these machine learning algorithms? And no. The majority, the overwhelmingly vast majority of companies do not need and never need to write machine learning algorithms. Instead, we find a machine learning algorithm that somebody else has already written, and we feed our data into it. But Simon, you say, you're telling me we just pick some machine learning thing off the shelf and we just feed a bunch of our data into it? It's a bit oversimplified, but yes. That's exactly what happens. And it's the same way that if you wanted a database, you're not going to write your own. You would choose an existing database management system that you could use. If you wanted to make a website, you're likely to choose an existing web framework or hosted web server. And when using machine learning, it's the same. The vast majority of people will choose an existing machine learning platform or framework to use. And there's a lot of these, both commercial and open source. For example, you could use some of the cloud-based hosted machine learning platforms like Azure has a machine learning. We have one at Google Cloud has its machine learning engine, as does Amazon, as does Alibaba, as does IBM. You're getting the picture, I think. All of these services provide frameworks and a set of tools to help you do this. And with multiple machine learning algorithms, you can pick and choose from and apply to your data, depending on what kind of task you're trying to do. And this has been the biggest enabler of the huge growth of applied AI in the last few years, is the combination of having these machine learning frameworks ready to go, together with easy access to all the computing power in the cloud, where you only pay for what you actually use. So it's reduced the barrier to entry. It's made it much, much simpler to start doing this. But even though we might not write the machine learning algorithms, there is still a lot of work to do. You can't just take all of your corporate data, feed it into a machine learning algorithm and expect it to understand everything for you. Let's say somebody handed me a flash drive with a year's worth of very detailed website activity data about our customers and their purchases and their behavior. Now, I could probably use this data to help identify fraudulent purchases, or I could use the same data to try and identify customers with high value, or use the same data to help identify hacking attempts. There's a lot of different information that was buried in this, but to find it, we have to understand what it is we're looking for. What are we trying to train the model to recognize? What are we trying to get the machine to learn? And the most important part of the entire machine learning process is preparing your data, understanding what you're looking for, and then filtering your data, cleaning it up, labeling it. Because if your data is full of garbage with invalid values and missing information and contradictory information, it doesn't matter how good the machine learning algorithms are. As ever, it's programming. You put garbage in, you get garbage out. Now, if you have a classic team of people working on machine learning projects, That's one of the responsibilities of the data scientist, is to take the raw data and to first transform it into something meaningful and useful before we take it a step further in the process. Now, after that, choosing this correct machine learning algorithm and putting the data into it, configuring it, testing it. This is another part that takes time and attention and, importantly, understanding what you're trying to accomplish. Most data scientists would tell you that picking the algorithm is not a single task. It's a process where they'll experiment with different machine learning algorithms, testing them with the same data to try and figure out which algorithm is going to give the best results for that particular problem. But in an introduction like this, we can only kind of scratch the surface. If you excuse the shameless plug, if you're interested in knowing a little bit more, I do have a full machine learning executive briefing and overview of this process, which is available at Pluralsight. But enough of that. Let's talk about some other kinds of AI. Now, earlier, I pointed out the visual cliche of the wireframe brain, and I said that a lot of the recent successes of AI didn't take that approach. They weren't trying to model a brain. They were using methods from statistics and probability. However, just as machine learning is a subset of AI, there's also a subset of machine learning called deep learning. And this does use algorithms that are more to do with the brain. These algorithms are called neural networks or artificial neural networks, which distinguishes those from the real neural networks that are inside our skulls. Now, it would be an exaggeration to say that these algorithms are actually modeling a human brain. They don't. It's more accurate to say they're inspired by a teeny little part of it. The idea that our brains have billions of neurons and synaptic connections, neurons with multiple connections to other neurons. And an artificial neural network, this idea is somewhat modeled. There are simulated neurons, these individual small nodes that can be connected to and send messages to other little simulated neurons. And where each of these little neurons is capable of performing some tiny little calculation as data flows through it. Now, in a neural network, it's made of multiple layers. There's always an input layer and an output layer to get data in and out. But typically in between the two, there's usually one or more hidden layers. When there's more than one layer, we call it a deep neural network. Now, if at this point you're thinking, I don't know exactly what I'm supposed to do with that knowledge, that's fair enough. The point that I'm trying to make is that this is still a form of machine learning. And that means we still have to provide examples of the results we're trying to get to. We're trying to say what success looks like, what we're looking for. And as we do this, as we feed examples into a neural network, it'll take these data and start passing it through the different nodes and doing it again and again and again. And as small transformations are applied to our data, the output from the different nodes will lead to results that are either closer to what we're looking for, in which case the outputs become weighted and more successful, or the results go further away from what we're trying to get to, and those connections become minimized and devalued. Now, if this sounds all a bit abstract and high level, well, it is, because to be honest, there's not much further I could go into neural networks without starting to say things like stochastic gradient descent and back propagation, and this isn't introduction topics. So instead, let's focus on this. What's it good at? And these deep neural networks, what has given us the best results in really complex situations like image processing, facial recognition, speech recognition, complex game scenarios. It is capable of very impressive, very profound results. But there's a couple of downsides, because training a deep learning neural network model can be much more computationally intensive and take a lot longer than some of the simpler machine learning methods. Part of that is that deep learning often requires a lot more data to train properly. Now, it's always difficult to say exactly how much data you need to train any AI model. It's very situation dependent. But with deep learning, it certainly wouldn't be unusual to expect to have tens of thousands or even hundreds of thousands of examples in order for that deep learning model to be trained well. But once that model is trained, it can be extremely powerful. So deep learning is often used for things like speech recognition and understanding language. And this is itself its own specific area of artificial intelligence. Natural language processing, or NLP, is that area within AI that deals with recognizing, understanding, analyzing it, even emulating all the different ways that humans communicate, using either voice or text or both. These days, you don't just see it, the NLP term, you'll see NLU for natural language understanding and NLG for natural language generation. Really, these two are just refinements to make it clearer about the direction that any communication is happening. So if I'm speaking to or writing to the computer, then it needs to understand my natural language understanding. If it's going the other way and the computer is constructing voice or text to talk to me, then it needs to generate that natural language. So natural language generation. And a great example of this situation where the computer both needs to understand what I'm saying and generate language to talk back to me is when you use any of the various personal voice assistants. I don't want to wake up any device you might have, so I'll say voice assistants like, or. But when you talk to these devices, it's far more than just speech to text. It is much more than just basic dictation, that can a computer recognize a stream of individual words? No, the computer needs to parse and understand what it is I'm actually talking about and the variety of different ways I might phrase the same thought. The goal of natural language understanding is about identifying the meaning, the semantic content of a sentence, even if that sentence is not well formed. We've got to understand, what does this mean? Is it a question? Is it a command? What is the subject? What's the keywords? What's the tone? What's even the sentiment or emotion? So in an example, I might ask one of these devices, do I need an umbrella tonight? Well, that question is actually about the weather, but I didn't say that. But we still expect the computer to understand it. Now, it's very easy to think, oh yeah, but my company isn't creating a new voice assistant, so none of this applies to me. But it probably does, because the ability for AI to understand and generate natural language is becoming increasingly common in even basic customer support situations, in marketing and social media. You have situations where you need to identify, say, the sentiment of a particular comment. If you have people writing reviews or commenting on your products, you might want an automated process that could look at any of these and understand if it's a happy user or neutral or angry, and if there's anything we need to do about it before it becomes a real issue. Beyond that, in customer support, we're seeing AI used to help us generate conversational interfaces, often called chatbots. These can be embedded in a web page, as you've probably seen, or in a social network like Facebook, or you could even interact with them using SMS text messages. But while early chatbots were really formulaic and scripted and frustrating if you stepped outside of the boundaries of what was expected, they're becoming more and more capable at dealing with many of the more repeated and predictable customer interactions. And it's also becoming very common to integrate our applications with voice assistants like or. Think about how expectations have changed over the past few years, where an application, a piece of software, might have begun as a desktop app, but then everybody started expecting, where's the web interface? And then they all started expecting, well, where's the mobile interface to interact with that? And now we're getting to the point where people want conversational interfaces, ways to talk to the same application. But thankfully, if we want to do this, we don't have to build all this technology ourselves, because just as there are general machine learning frameworks we can use, we now also find multiple options to build or integrate these conversational user interfaces. For example, if you're using the Amazon services, they have something called Amazon Lex, which helps you build these interfaces. If an iOS developer could use Apple's Siri kit to integrate voice capabilities into an iPhone or an iPad app, Microsoft Azure has a language understanding service, as does IBM with Watson. Again, you kind of get the picture. You can expect any AI platform will offer some kind of specialized service about being able to do this. And this is all just another example of what I said earlier in the machine learning section. The main reason for the incredible growth in applied AI over the last few years, the biggest enabler of all of this has been the large commercial cloud service providers that offer all these capabilities. Now, the order of these top companies changes slightly depending on where you are in the world, but let's say Microsoft Azure, Amazon Web Services, Google Cloud, Alibaba, IBM, Oracle. There are others, but let's leave it at that. These all offer a variety of pay-as-you-go artificial intelligence services you can tap into, ready to use together with the computing power that you need to use them, but where you don't have to build your own AI data center, you just pay for what you're using. And all of this has vastly reduced the barrier to entry, made it much simpler to get started. Now, you certainly don't have to use any of the commercial cloud-based providers. There are open source machine learning platforms and frameworks as well. There's things like TensorFlow, which you as a developer could download and install yourself. Another example is PyTorch, which also a machine learning framework. And when I'm talking to people who have some programming experience, but don't have any experience in AI or machine learning, I am often asked what the most common programming language that I should use for all of this. Now, recommending a language is always a contentious task, but for anyone who has some background and looking to take the next step with AI or machine learning, or even just to experiment, my default suggestion is straightforward: Python. Now, yes, there are other languages popular in the AI community, and if you're already working in an environment where you know there's a specific technology that uses another language, like R, for example, is another common programming language, then sure, use that. But if you were doing that, you'd already know, so you wouldn't be asking which language to use. So if you're asking, then Python is never a bad choice for any of this. But if someone is intending to take the next step, there is one more aspect, which is not just how to do this, but how to do it responsibly. Because we started all of this discussion talking about some cliches, we're going to end it with another one, that AI is incredibly powerful, but with great power comes great responsibility. And we've become very aware in recent years of harmful consequences of some AI, sometimes intentional, sometimes unintentional. One of those unintentional side effects is algorithmic bias. A well-publicized situation is where machine learning was used to try and streamline a recruitment and hiring process. So we could use it to find good candidates more quickly and weed out bad candidates. So the model was trained with years and years of actual data, resumes, and information about the qualities of successful candidates. This was in computing, which is historically male-dominated. So just on pure numbers alone, most successful candidates over the last 10 years were men. And that unintentionally became part of the model, what the machine learning app was looking for. What does a successful candidate look like? Well, most of the time it's a man. So if this new candidate doesn't match that description, well, score them lower. And this was a situation where there was no human prejudice, no intentional effect. It was just the nature of a historically male-dominated profession, but where the model can end up not just reflecting, but reinforcing that disparity. But figuring out that algorithmic bias is even happening can be very difficult, because one of the very real issues with many algorithms in machine learning is that when you train a model, what you then get from it will be an answer, a result. But what you don't get is an explanation of that answer. This is sometimes called the black box of machine learning or of AI in general. You train a model with existing data, You then feed new data into it. The model then gives you a result. Candidate A is rated 5 out of 5. Candidate B is rated 2 out of 5. Why? Well, it doesn't tell you why. You get the result, but you don't get the explanation. And if you have an unquestioning culture of, well, that's what the computer says, then you might end up institutionalizing biases in the system without realizing that's happening. So we should always be looking at this as a tool. This is a helper. Artificial intelligence is meant to help us understand the data, not to understand it for us. We also have techniques like deepfakes, where AI can be used for intentional deception and disinformation. A deepfake usually refers to a video, but this could be an image or even an audio recording. But where AI is being used to either replace a person in a video or make it seem like they said something that they didn't. And you're seeing more and more of these appear in different news stories. Deepfakes are typically made using those deep neural networks I talked about earlier. They generate extremely realistic results. And because of these and other situations, there are now various initiatives around ethics in artificial intelligence and responsible AI. There's groups like partnershiponai.org. This has got over 100 member organizations, including Apple, Microsoft, Amazon, Google, Accenture, and they're trying to develop guidelines and best practices about safety and transparency in artificial intelligence. Because going back to that very first cliche that AI always ends up wanting to kill everybody, well, we have had folks like Bill Gates, Elon Musk, Stephen Hawking, all raising serious concerns about what's likely to happen if we don't think about how to create ethical, responsible AI well in advance. Or, as Professor Hawking said, success in creating AI would be the biggest event in human history. Unfortunately, it might also be the last. Interesting times ahead. Anyway, we are at time, I said about 45 minutes, so thank you for joining me and listening to me rant about this. I hope you enjoyed the talk. If you are interested in going deeper, we have plenty of courses at Pluralsight on various aspects of machine learning, data science, and of course, we have our Pluralsight Live conference coming up in a few weeks, and that will be free this year. So plenty of resources to check out. So thanks again, and I guess I'm going to open it up and see if there's any Q&A. If not, that's great, and thanks a lot.
Yeah, thank you again, Simon. Really much appreciated on that. If there are any other questions, feel free to click that Q&A button at the bottom. We have just a couple minutes and see if we can get to them.
Oh, it's fine. I'm going to presume that I just answered everybody's questions about everything. But hopefully, the folks who are watching, I hopefully gave you at least a few resources that people could use to have an idea of where to go. So this, this wasn't ever going to be a particular Q&A heavy presentation about one particular aspect of the technology, but hopefully as a general intro, it was useful. So.
Well, I myself found it perfectly informative, exactly what I needed. So
Great.
Simon, with that, thank you very much. And as well to our audience members, we appreciate your time today. Hope you enjoy the weekend.
Great. Thanks very much. Have a good one.